Hello, I would like to welcome you to lecture 17 of 2EE to FH3. In this lecture, we'll discuss the method of images and its applications, and this coming from the last part of chapter 6, pages 256 to 267. I should mention that by this part, we conclude the electrostatics, so this will be the last part we discuss electrostatics. And then we move in the following lecture to discuss basic steps of magnetostatics. Now we'll start first by mentioning what is the method of images, why it's important, and how it's used in electromagnetics to simplify many problems. In a previous lecture, we discussed the uniqueness theorem. We said if we have a certain region in space, something like this. It has some charge distribution Q inside, so there is some charge here rho V inside, and we have boundary condition. If this is V1, this is V2, we are imposing some boundary conditions. Some of these voltages are 0, some are 5 or 4 or 3, some numbers, or some boundary condition, whatever. Then the solution inside this region is unique, meaning that the potential at every point here must have one value. You cannot have two solutions. You cannot have V1 and V2. And if we have V1 and V2, they must be equal at every point in the space. So this led to the thinking that if we have some difficult problems where we are not able to solve easily, then why don't we replace them by simpler problems that has the same boundary conditions and then the same solution? This really the main concept behind the image theory. If you have a problem, it's extremely difficult to solve. What if we keep the same boundary condition, keep the same charge distribution? Then in that case, the solution inside the region of interest will be the same. And in that case, we can solve an easier problem. And the way to keep the same boundary condition is to use image charges. And this is why the method is called the method of images. Because it actually creates image charges, line charges, point charges, volume charges, dipole images, current images. They replace an element by its image, and then in order to satisfy the boundary conditions. This approach is best illustrated through a simple example. We have here in this example a discrete charge Q, point charge Q. It is located at a distance h above an infinite ground plane, like Earth. Earth is an infinite ground plane because it's a conductor. Because Earth is huge, you cannot give it enough charge to change its potential. So potential is zero. Its potential is zero. Okay. We talked before about the potential resulting from a point charge. And we said that the potential resulting from a point charge is given by the expression V is equal to Q over 4 by epsilon R, and R is the distance from the charge to the point where we are measuring the potential. But this expression is valid only when the charge Q is away from any other charges. If there are other charges, you have to include their potential as well. When we bring a charge like this one close to a conducting plane, what is happening is that this charge will induce negative charges on the surface. Why are these charges induced? Because you have to maintain that the potential here on the surface is equal to 0. But this charge is trying to give every point here on the surface a positive charge. Then these surface charges will appear, and they will create their own potential to cancel the potential resulting from Q every point here, to give you a zero potential on the surface. And by the way, this distribution of charges can be high nonlinear. We don't know. It's not a uniform charge distribution. They are not uniformly spread. Actually, in this area, very close to the charge, there's going to be very strong charge density. And far from the charge, say here or here, the charge distribution will start to go down. So how do we solve a problem like this one? We have a charge Q that we know, and we have a surface charge distribution that we do not know. It's an extremely difficult problem to solve. Now, we can try to solve a simpler problem. What's the simpler problem? We can keep this Q as it is, and then we try to remove this ground plane and add other charges that gives total potential here of 0 with Q. So they try to cancel the field resulting from Q. We try to create an image charges that would cancel the potential. So by doing that, we maintain the same boundary condition. So V is equal to 0 in the plane. It is the same charge distribution. Then the solution here, V is going to be the same like the original problem. And this problem actually has been solved long time ago by scientists. And the solution is simply to obtain, to put a negative charge Q here at the same distance h from that plane. So this is how the equivalent problem looks like. We cannot solve the original problem because we don't know what is the charge distribution on the surface. But we know that the potential here has to be equal to 0. It's a boundary condition. So what we did, we created this negative image charge. It's a fictitious charge. It's not a true charge. Its value is minus Q. What is happening? Every point in this plane is in the same distance from minus Q as the same distance from Q. So they cancel each other out. And they give total of 0 potential everywhere here. So by doing that, we maintain the same boundary condition. The charge distribution in the top half space is the same. Then the solution here is going to be the same. And what is the solution? If you want to get the potential anywhere here, it is the sum of the potential resulting from the plus Q charge and the negative Q charge. If you want to get the electric field, it is the sum of the field resulting from the negative Q charge and the positive Q charge. And so the solution, the top part, is the same. Now, I have one word of warning. In the original problem, there was no lower half space, so this was metal, and the field inside it was 0. It was a perfect conductor, grounded perfect conductor. So the field inside was 0. But here, if you try to calculate at any point, there will be field, but this field is fictitious. So what I'm saying is, the solution is true only for the top half space, while the bottom half space, where it's really a fictitious part that we added to keep the same boundary condition, the solution there is not related to the solution of the original problem. Only the solution in the top half space is valid, because this is where we maintain the same boundary condition, 0 voltage, and we maintain the same charge distribution. Of course, once we remove the ground plane, if here we had air, here we also have air. So it's air everywhere. There is no conductor anymore. Now it's a simple problem of superposition. We can use it to calculate the field. And you can see here the field line looks something like this. They are pointing from positive to negative charge. And of course, in the original problem, we have surface charges. And in the original problem, the field lines starting on the positive charge are all terminating on these surface charges. So this is exactly the same thing. For the top part, it is exactly the same problem. So we apply superposition. We proceed to calculate all type of quantities in the top half space. We can get potential, we can get electric field, we can get displacement vector, we can get even the surface charge density here by calculating the normal component of the vector D. So for the equivalent problem, we don't have any conductor. Here, if we had epsilon in this part here, if we have epsilon naught, then it's still epsilon naught here. Here is also epsilon naught. There is no conductor anymore. The same boundary condition. Then we have now, it's a superposition problem. We have a charge positive Q located at 0, 0, and H. This is the x-axis, so this height is H. And we have a negative charge located at 0, 0, and minus H. These are the two charges. Then the field everywhere in the top half space, you can see Z is greater than or equal to 0. This is the only valid region, because this is where we maintain the same boundary condition and the same charge distribution. Is the sum of the field resulting from the positive charge and the field resulting from its image. Now we know what is the field resulting from any charge. It's Q over 4 pi epsilon naught R minus R dash over modulus R minus R dash to the power 3, where R dash is the location of the charge. So the location here is 0, 0, and H, and this is my observation point or field point. It has location X, Y, and Z. So when you subtract them, you get X, AX, Y, AY plus Z minus H in the Z direction. This is a vector R minus R dash. This is R, and this is R dash, or this is what we call the vector R1. It's the vector here R1. And then you divide by the modulus of this vector raised to the power 3. So you can see we square every component to the power 1/2, and then we raise it to power 3. The same thing will happen for the negative charge. It is located at the location 0 and 0 and minus H, and this one is X, Y, and Z. Then this vector, which is pointing from the charge to the observation point, is equal to X, Y, and Z minus 0, 0, and minus h. So it gives you this vector x plus y plus z plus h az. And then you divide by the modulus of this vector to the power 3. The field everywhere, any point in the top half space, is the sum of these two fields. Now, one point or one region of particular interest, what is the field here on the surface? The field here on the surface is not zero. You have, on the original problem, we had a ground plane, but normal components of electric field are not zero in ground planes, only tangential components. And this is the case here. If you try to sum them, both z equal to 0, if you put z equal to 0, and then you sum these two, this one has a negative sign, so this will give you minus QH. This one has a positive sign with a negative multiplied by minus h, will give you minus QH. Then the answer will give you minus 2QH over 4 pi epsilon naught in the z direction, which makes sense because the electric field will have to be normal to the conductor. Okay. Now, if you want to get the charge density, we agreed from boundary conditions that we discussed earlier that the normal component of D here, normal component of normal to any conductor, will give you the surface charge density at this point. So we simply multiply this component by epsilon naught, and then this will give us the surface charge density. And of course, surface charge density must be negative, because this is a positive charge, and this positive charge will induce negative charges on the ground plane. So this is what we have here. We calculated D by multiplying at z equal to 0. So on the ground plane itself, we calculated D from E by multiplying by epsilon naught. And then we agreed that the surface charge density at any point on that ground plane, remember it's an infinite ground plane, it's infinite in the x and y direction, will be equal to d normal. And d normal here, which is in the z direction, the normal to the plane in the z, so this is the normal component here, is minus QH over 2 by x squared plus y squared plus h squared to the power 3 over 2. So as you could see, indeed the surface charge density is very complicated. It has dependence on x squared plus y squared. If I want to get the total charge on the surface, what I will have to do, I will have to take this rho s and then integrate it over the whole ground plane from minus infinity to x, from minus infinity to y. And this integral can be done. The book shows details of this integral. You have to convert it to rho, then x squared plus y squared becomes rho squared, and then you replace dx dy by rho d phi. Your integration will be rho from 0 to infinity and phi from 0 to 2 pi. If you carry out this integral, you will find something very interesting, that the total charge on the ground plane is equal to minus q, is equal to the negative of the positive charge, which is equal to the image. So the image really that we put there try to represent the effect of this distributed charge, which is distributed all over the ground plane. So, and this actually should be expected as well, because we have flux, it's diverging from a positive charge q, then it should terminate on a net negative charge of minus q, which is really distributed all over the whole ground plane. So this example is very interesting. It shows you how using an image makes a problem extremely simple. Without using an image, we had no clue of determining this nonlinear surface charge density, which is varying from one point to another on the ground plane. And the problem was extremely complex. But by maintaining the same boundary condition, the same charge distribution in the original region, we're able to solve it. Now, let's take a look at a couple of examples. The first one is this example here. We have a charge Q located close to two infinite grounded conducting planes. So this is similar to the previous problem, but here we don't have one boundary condition, we have two boundary conditions. And here we assume this is the x and z plane. We assume that the charge is located at location A in the x, B in the z, and 0 in the y. So assume that this is the y equal to 0 plane. Of course, this problem is extremely difficult to solve using normal techniques. If the charge was alone in free space, it's fine. The potential everywhere is q over 4 pi epsilon naught r. But because you have the charge close to ground planes, to two ground planes, the situation is completely different, because these ground planes must have 0 potential, but this charge is trying to to make them have positive potential, because the potential here resulting from this one is Q over 4 pi epsilon r. You have to measure this distance. So how does this is balanced? Well, these conductors will have lots of charges available on them. Q will induce on the surface some negative charges like this, and these negative charges will create their own potential, and they will cancel out the potential resulting from Q at every point on this infinite ground plane. So this is what you get here. You get also negative charges, and of course the electric field are going to be normal. So this is what's happening. These induced charges are induced negative charges on the surface, and they are what balances the effect of this charge. But we don't know their distribution, we don't know their values. It's extremely difficult to calculate the field everywhere. But we can do something else. We can simply maintain the same boundary condition, try to keep 0 here on this plane, try to keep 0 here on this plane, and keep this charge as it is, Q. In that case, the solution in this part of the space, the positive x and positive z quadrant, will be the same. It will not change. It will be the same. Nothing will change. The solution will be the same. So the idea here, if we have a charge Q here, why don't we add a minus Q charge somewhere here in the bottom? So I can simply add a minus Q here, and then on the other side I can add another minus Q as well. So I can add another charge at the same distance. So let's see this what actually I will do in the next slide. So this is just to summarize. This is summarize what we have said so far. A positive charge, because it's close to a ground plane, it will induce negative surface charges to keep 0, to keep the potential 0 at the ground planes, and we need images. So we'll create two images. One image to maintain 0 in the horizontal ground plane, another image to maintain a 0 potential in the vertical ground plane. So this is the situation we have here. You add the charge minus Q at a distance B. If this was B, this will be B. So these two will cancel each other along this ground plane. And they add the charge minus Q at a distance A from the vertical plane. So if this was A, this would be A as well. So this charge Q and this charge minus Q, they cancel each other out on the normal plane. But now we have a problem, because this charge minus Q will damage the balance in the vertical plane, and this charge minus Q will damage the balance in the horizontal plane because each one of them balances one plane but damages the other. And scientists have solved this problem a long time ago, and they said the solution is to add one more image charge. So we have a charge plus Q here, and as you can see, if this distance here was A, this is the z-axis, this one would be A as well. If this distance was B from the x-axis, from this plane, this distance would be B as well. The great thing about this three image charge configuration is that this charge and this charge, they cancel each other out here. This charge and this charge, they cancel each other out here. Okay, the plus Q and minus Q, they cancel each other out in the horizontal plane. The minus Q and the plus Q, they cancel each other out in the horizontal plane. So now we maintained that the potential here is 0 at every point. The potential here is 0 at every point. The same charge is here in this part of the space. Then the solution will be the same. The solution is going to be the same by using the uniqueness theorem. So now if you want to calculate the electric field at any point here, any point inside this region here, simply sum the electric field coming from these four image charges. One word of warning, and I'm repeating it again. There is no field here. There is no field here. There is no field here. These are all fictitious regions. Even though we remove the conductor, and if this is epsilon naught, this is now epsilon naught, this is now epsilon naught, this is now epsilon naught. It's air everywhere. Or if it is epsilon, it's epsilon everywhere. Okay, but these are fictitious regions because this part has nothing to do with our original problem, because we added a charge that wasn't in this part before, which is minus Q, and here we added a new charge. So the field here is not related to the field of the original problem. Only the field in this part, where you can see the x and z are positive, is related to it's the same as the solution of the original problem. This has to be very clear. So this problem was solved, this problem of a charge near two orthogonal ground conducting ground planes was solved by scientists many years ago, and the solution is to add 3 negative charges. So now we have superposition. We have a charge plus Q located at location A, 0 and B, and I will call this charge for simplicity Q1. We have a charge minus Q located at minus A, 0 and B, and I will call this charge Q2. This is the image along the x-axis. We have a charge plus Q located at minus A, 0 and minus B. This is the image when I reflect along both Z and X. We have another charge minus Q at A, 0 and minus B. I call them Q1, Q2, Q3, Q4. I know the value for every charge. It's Q. Q can be 1 nanocoulomb, 2 nanocoulomb, 3 microcoulomb, whatever the value may be. And then we apply superposition to get the field or the potential or any other quantities or the surface charge that we are looking for. So if I ask you to calculate the surface charge, very simple. Calculate the vector E at the plane, calculate the vector D, and then get the normal component. This will give you the surface charge density. Integrate the surface charge density to get the total charge. So here in this example, I'm just asking for the total potential. So the potential at any point here, V, is the sum of 4 potentials. The first one resulting from the charge Q1, the second one resulting from the charge Q2, the third one is resulting from the charge Q3, the fourth one is resulting from the charge Q4. I simply calculate these distances, and these distances are very simple because this is a point. This point here is any point that has 0 y, so it is x, 0 and z. Any point here is x, 0 and z. While this point here is A, 0 and B. This point here is minus A, 0 and B. This point, this one, of course, these are x and z. So this one here is A0 and B. This one here is minus A0 and B. This one here is minus A0 and minus B. This one here is A0 and minus B. So I know all the coordinates. I apply superposition to get the total field, to get the total potential here. In this case, the potential here is the sum of all 4 potentials. So the distance R1 is the distance from this point, which is x, 0 and z, to this point, which is A, 0 and B. And this is really why here doesn't show. So this is the distance R1. This is distance R2. You can see here the only difference that the x coordinates is negative, so minus A, so this becomes x plus A, and so on. You do the same for R2 and R3, and you can get the potential anywhere. As shown here, these are the last 2 distances, R3 and R4. And once I give you a value for A and B, these are simply calculations. I can give you any x and z. I ask you to calculate the field at x equal to 1 meter, z is equal to 1 meter, where A and B are equal to 25 centimeters and maybe half a meter. You can put any number there. You will be able to get the total potential resulting from these 4 charges. Now, let's consider one more example. We would like to calculate the potential at any point x, y, and 0 due to a dipole of momentum P located at 0, A, and 0 when the xz plane is a grounded conducting plane. And we assume the dipole is in the xy plane. So here we have an electric dipole. We talked before about electric dipole. Electric dipole is simply 2 charges, one positive, one negative, separated by a tiny distance d. And we said that this is used very often in electromagnetics, and we used it when we talked about polarization as well. So now we have a dipole. It is located in the xy plane. So both charges are on the xy plane. It has a dipole momentum P, and we agreed the dipole momentum is nothing but QD, where Q is the value of the charge, any one of the 2 charges. One is positive, the other one is negative, and D is the vector pointing from the negative to the positive charge. And the dipole is located at 0, A, and 0. So let's first start by drawing a geometry to see how the problem looks like. So here we have the case. This is a dipole here. I'm not sure whether it's clear or not. It's pointing this way. Okay, this is a dipole. This is its negative charge. So there's a negative charge here. This its positive charge. The center of the dipole is located at a distance A from an infinite ground plane. So this is the xy plane. Now, if the dipole was away in free space from any conductor, and we discussed that before, we were able to derive an expression for the electric field and potential resulting from the dipole. But once you put it close to ground planes, things become completely different, because this is an infinite plane. It has a zero potential, like Earth. Earth has zero potential because in order to give Earth any voltage or any potential, you must give it infinite charges. It's a huge volume. So Earth is usually taken as zero potential. So here this is a grounded infinite plane, and when you put it beside it, this dipole is trying to create a potential here. But what will happen is that this plane will respond by creating a very complex distribution of negative or positive charges. We don't know. It will create a very negative, very complex distribution. And this distribution, complex distribution of charges, will cancel the potential resulting from the dipole every point on this plane to give you zero potential. Again, this problem is extremely difficult to solve. We have no way of knowing the value of the charge density induced here on the surface, and we have to find a simpler way of solving this problem. And the simpler way is to remove this ground plane and create an image that will give us zero potential along this ground plane, and then the solution here will be exactly the same. Now, I want just to remind you a few things about the dipole. Dipole means you have a negative charge and positive charge. They are located very close to one another. Dipole moment is a vector pointing from the negative charge to the positive charge. Its value is equal to QD, where D is a vector pointing from the negative to the positive charge. Now, when we create an image for the dipole, I will create an image for every one of the two charges. So this negative one will create a positive image here, and this positive one will create a negative image here. This is what we agreed. We can calculate images for point charges. So if you do that, this is how things will look like. So this is the original dipole, is pointing this way. This is the image dipole, is pointing this way. You can see here because this is negative, its image is positive, the same distance. This is positive, its image is negative. The dipole moment now has changed. Over here it had a positive x and positive y components. Here it has a positive y and negative x components. So what is happening is that because of this change, and as we agreed, this is the x-axis, and this one here is the y-axis. Okay, this is y. So as we agreed, we could see what's happening here. The x component reverse direction. So if you try to project this vector here, you can see it will give you two components. It's positive x and positive y. But if you try to project this one will give you negative x and positive y. And this negative x vector has a negative sign to that one. So the result of this image is that the x component of the momentum was rotated by pi. It was multiplied by a negative sign. So the dipole moment is a vector. So I can give you it. In this case, it is in the xy plane. So it has a bx in the x direction, a by in the y direction. Then the momentum of the image will be minus bx in the x direction plus by in the y direction. And this is resulting from this factorization. The y component remains the same, while the x component reverse direction. Here it was in the positive x, while here it's the negative x. So this is, now we know what is the image of this one, and this image will maintain a zero potential everywhere along that plane, and thus I can get exactly the same solution. Now, if this dipole is located at 0, 0, and a, so its center at 0, a and 0, so y is a here, then y would be minus a here. And then we can continue our calculations and apply superposition. The field anywhere here, or the potential anywhere here, is simply the vector sum or the scalar sum of the field resulting, or the potential resulting from the first dipole and the second dipole. So we apply superposition. We agreed in earlier lecture that the potential resulting from a single dipole is given by the dipole moment dot r minus r dash, where r minus r dash is the vector pointing from the center of the dipole, which is r dash, to the observation point, which is r. So this is the observation point here. It's x, y, and 0. I assumed it's in the xy plane. And this divided by 4 pi epsilon naught modulus r minus r dash to the power cubed. And because I have two charges, I have to calculate two potentials. The potential resulting from the first dipole, which I call it V1, and the potential resulting from the second dipole, which I call it V2. So when you sum these two together, this is the expression for the first potential, the expression for the second potential. I know what is B1. B1 is given to me as a vector. It has x and y components. I can calculate this vector. It is a vector pointing from the point 0, a and 0 to the point x, y, and 0. I can calculate that, and this is expression. I can calculate this vector, which is r minus r2 dash. This vector here is r minus r2 dash. It is a vector pointing from the point 0 minus a and 0, which is this one, the center of the image dipole, and this point, which is x, y, and 0. So this one here is the vector r. By knowing all this, I know B1. I know I calculated B2 using B1. I can get the potential anywhere in the top half space.